Greetings, everyone. Thank you for joining us today for what I believe is the fifth in a series of webinars on the topics of load forecasting and resource adequacy. So today, we're going to be covering the topic of resource adequacy analysis, providing some basic overview of the concepts and issues and topics that are covered in resource adequacy. My colleagues from the National Renewable Energy Laboratory, Jose Lara, Sebastian Machado, and Rafael Monge, and Allison Campbell and Aran Schweitzer from PNNL have developed the material you're going to see today and presenting to you. Go to the next slide. First and foremost, we want to thank our funders at the Department of Energy for making this webinar and the entire series possible. Let me talk a little bit more about this series of where this one fits within. We've had a series of webinars that we've held over the last several weeks and one more to go on the next slide. We kicked off the series back in early mid-October, providing an overview of it and really trying to connect the topics of load forecasting and resource adequacy to sort of the broader state planning efforts that many states are undertaking right now. We then moved into focusing into forecasting and provided first a general overview, and then moved into some specific issues, topics, techniques, and models associated with forecasting for load expansion, and then subsequently forecasting for distributed energy resources. After that, we are now turning towards the topic of resource adequacy. And so today we'll be covering, like I said, the basics of resource adequacy analysis. We then will be turning in a subsequent webinar to transmission and distribution system planning, again, providing some basic overview. And then for the final one of our webinars, we will be looking at the evolution of resource accreditation. And so with that, let me hand things over to colleague Jose to get things started.
Thanks, Pete. Thanks for the introduction. So we're going to discuss today resource adequacy, which in a way, it allows us to measure the ability of the system to meet electric power and energy requirements within acceptable limits. So considering that the units actually go offline, the availability of these units changes over time, and it is fundamental philosophy that came from resource adequacy, as it was invented through the 70s and the 80s. And the idea was that when you need to calculate the sweet spot between how much reserve do you need to keep, how much do you invest, how much capacity you have to build, you need to take into account this risk measurement element of how much can the load increase and how much can the load change depending on the requirements of the system, and how much you need to keep taking into account this lack of availability of the units. So in the classical resource adequacy literature in the 70s and the 80s, the main source of uncertainty was outages. And in many ways, that was the big question. How much is the load going to grow and how are my outages going to happen? However, if you look at the slide, this is exactly what you can see, right? Like there's a total installed capacity and the reserve calculated over those amounts of capacity and how much are the outages. So resource adequacy in many ways was defined as the measure and the ability of the power system to meet electric power and energy requirements within acceptable technical limits, considering these scheduled and scheduled outages. Now we go to the next slide. We see that as the power system has evolved, we started to increase resources that are variable. So we have now more sources of uncertainty and more spatial correlation. We go to the next slide. Then we have this component of how does this uncertainty starts changing around the availability of resources and the continuous meet of the peak with the availability of the renewable and the changing resource schedules. We also have the next changing is that because since the 70s and the 80s, power systems have increased in size and widened in area, now we have more correlation between the different components in the system. So outages that happen in relatively far away geographical locations can have an impact in a local system. And if we continue, and then the introduction of storage and batteries is fundamental and introduces into the resource adequacy component some temporal coupling. How much actual capacity a battery can provide at any given time is fundamentally dependent on its state of charge. And we need to take into account all of these details. We go to the next slide. we can then take this risk assessment framework for resource adequacy. So we can define risk as the combination of the exposure and the uncertainty. And once we understand that mix of exposure and uncertainty, we obtain some metrics to see what is the impact in our system of this exposure and the fact that certain events can happen. So the exposure, we can classify it into big buckets. One that is systemic. Those are all of the exposures that say I can have cascading events. I can have situations where one fault in one part of the system affects the other. We also have idiosyncratic exposure, which is the unit level, the single component type of failure. And we also have uncertainty that could be knowable or it can be unknowable. So knowable are those uncertainties that we can actually characterize with distribution of some sort, like for example, outages. And the unknowable are those big uncertainties that happen in the tails or that are difficult to characterize with probabilities and provide a detailed representation for risk assessment. So we'll go to the next slide. So if we take these big methodological representations, we have to make decisions. And when a stakeholder comes into a resource adequacy statement, this analysis needs to have a good idea about what is the exposure metrics we want to include and what are the uncertainties we want to include. So in the case of an application, for example, to an IRP or to a planning process, stakeholders need to provide input about what are the operational representations that matter for my system. Do I care about some systemic issues that can lead to system collapse or to unit outages? So the definition of resource adequacy has this big challenge because it feels like everybody's doing different things. And the reason for it is because, for example, in Southern California, where forest fires are really important, the operational representation and the uncertainties that I need to include are very different than problems that I can have in the Northeast, where maybe one of the main sources of resource adequacy problems could be related to winter storms and cold weather. So whereas in the Southern California example, understanding the impact of transmission outages, considering risk fires, or that's not the same as lack of supply from gas, considering the cold weather, right? The same happens with the uncertainty. There's uncertainty that we have to define what needs to be included, right? Because otherwise an assessment can be anything can happen. So we can have knowable uncertainties like the outage rates. Those can be calculated from data sets like GATS. We can implement different types of distributional probabilities that we're going to discuss through this presentation. But there's also these unknowable type of events like the extreme weather. It is almost impossible to know if in 2030 there's going to be some winter storm or some heat wave coming through the system with which probability or which likelihood. So the approaches of what goes into a resource assessment framework requires this ongoing conversation with the stakeholders about what is the appropriate representation of the operations and what is the appropriate inclusion of uncertainty when the regulator or when the agency is trying to come up with essentially a risk assessment of the system. And finally, there's also an important component to be like, which are the different metrics that we care about during our assessment process so that we can actually also get metrics that matter for our system. Maybe a system is more prone to be worried about extended periods of time without potential energy versus big faults that can lead to short periods of time and are actually large amounts of loss of load. So even though this is not a comprehensive list of all of the operational details or all of the potential uncertainties, this framework allows us that when we do it ahead, we can then define what are the needs that we have to include into our assessment. So we go to the next slide. So for example, here we can understand some very basic mechanics of resource adequacy analysis. On the top line, we have like a system that has many periods that happen during long periods of time and high losses of energy. So it's a system that, given the three events that happen, we can see here the black line basically going over the blue line where the resources are available. So we have a relatively large number of hours with a relatively large time that these outages happen and large losses of energy. Then in the second one, we see a different makeup altogether of the resource adequacy challenges of the system, where we actually have 6 events. So there are many events that are small, and you only have big losses of energy in one of them. So again, we have a different type of solution has to go into our case A versus our case B. And finally, we have a situation in scenario number 3 when we have a small amount of events with a small number of energy losses. And finally, we have this third case that has, again, a single event with a single load and a single time period. So these type of systems have different makeups of resource adequacy challenges, and bringing, for example, a scenario number 4 to zero completely could be cost ineffective. So in this particular case, on average, these systems have about 575 hours, but they lose 875 megawatt hours of energy. And again, what we can observe here is that depending on your stakeholder requirements, some of these scenarios might be more or less acceptable. So we'll go to the next slide. And I'm going to pass it on to Sebastian, that is going to talk to us about the elements of knowable and representation of uncertainty.
Thank you, Jose. So going a little bit deeper into the resource adequacy methods and modeling approaches, the classical risk model focuses on quantifying the probability of component failures, and traditionally this is focused on the generation fleet. At its core, the model often relies on historical force outage rates that are then introduced into Markovian representation of the dispatchable generators. So the simplest Markovian representation consists on two states, as you can see in the figure, the state available or up and unavailable or down. And then you will have transition probabilities defined by the parameters lambda, the failure rate, and mu, the repair rate. So it is important to highlight that in this modeling approach, the transition probabilities are typically derived from historical datasets. While these datasets may be the best information available, it is important to recognize that past performance does not always reflect future reliability conditions. So parameterization should be treated with caution in those cases. And also, models often assume that force outage rates values are independent and uncorrelated across the generators and devices in general. So also it is important to recognize that in reality, correlated failures can occur, for example, during extreme weather or extreme understood. And we are classifying in this slide as a knowable. However, the parameters themselves may vary over time. So for instance, some ISOs, such as MISO, conduct separate studies for winter and summer conditions. And this acknowledges that while the underlying model is the same, the parameterization might vary across different seasons. So going to the next slide. So also from the perspective of uncertainty representation and resource adequacy models, variable renewable energy source introduce a new type of uncertainty that is continuous and correlated and directly tied to the availability of the primary source of these renewable sources. And traditional resource adequacy Markovian models were not designed to capture this kind of continuous probability functions. They were designed to capture asset availability in discrete states. So in practice, there are like two different approaches. The first one tries to represent with the Markovian model, tries to represent both sources of uncertainty. The availability of the asset itself and also the availability of the primary source. However, this often introduces modeling inconsistencies since the discrete states does not align with continuous probability functions. Another common practice is to rely on historical time series of renewal output. while this is a straightforward approach, this ignores the stochastic nature of the resource availability. Also, some other broader impacts of variable renewable energies on resource adequacy methods includes there is a shifting from gross peak load to net load because of the nature of these resources. Also, there is a need for higher temporal resolution because the uncertainty of the non-dispatchable source requires finer time granularity to capture short-term fluctuations. And also, because of that, as we introduce storage devices, that is very important to capture the sequential operations of these devices, for instance. So also there is, it is very relevant, like to keep chronological simulations in resource adequacy studies. So going to the next slide, I pass over to Jose again.
So one of the biggest challenges in the analysis of RA in modern power systems, especially when we start looking at the bigger correlations that are driven by weather, is this representation of unknowable uncertainty. So extreme events driven by extreme weather conditions, for example, the storms in Texas in 2022, you can see that they have several characteristics. One is that they drive big problems around multiple regions. So you have these kind of extended areas that will cause situations where multiple units can actually go offline at the same time. And that is more difficult to predict exactly when those events are going to happen and actually the value of those correlations. So this combination of rarity and high correlation of the events make them difficult to characterize in terms of probabilities and different metrics that we can put in the system. So do we have to answer questions that are difficult, like when can we expect a 5-day freeze with temperature below zero, right? So that we can, what happens if that is correlated with a particular combined cycle unit being in their maintenance? And again, we can also have more than short-term periods of, especially when we apply resource adequacy to long-term planning, when can we expect another 2-year drought like what happened in 2014, 2015 in California and lose 40% of our effective capacity of hydro? Those type of events have the same effect of reducing our total installed capacity that we can employ for generation of power and are more complicated to predict. So we have to take approaches where simulations are able to run and capture situations like that outside of the classical probabilistic mechanisms. We go to the next slide. Right, the other challenge here is that when these type of events happen, then the Monte Carlo approaches that are usually followed that use the central limit theorem start to be more difficult because you can't capture these type of events. So actually in the literature for resource adequacy, one of the weaknesses that the even original authors recognized was that if you run a Monte Carlo simulation like this, that gives you some probabilistic representation, you can have some understanding of the value of those distributions, but all of them have caveats, right? So it is very challenging to say that, first of all, we can capture how many scenarios we can capture to be able to get these events representation at the tail. So, you know, in the classical central limit theorem, you need to say how, it doesn't matter how many simulations I run, I might not be able to capture these type of extreme events and situations that happen, both because of the correlation and the rarity. So we have to understand the limitations of Monte Carlo approaches when it comes to capturing situations that don't happen very often. So I think that one important component of the resource adequacy is to, again, have this discussion with the stakeholders about how far can we take an analysis that employs Monte Carlo analysis to be able to have some security about our system's properties. We're going to go to the next slide. Yeah, and this is, again, like the whole discussion around the effect of fat tails, right? So extreme events are very rare, so we don't have enough of them to be able to characterize correctly the probabilities. And in some cases, it's almost impossible to determine that actually property at the edges, right? So if the probability is unknown, with sharp discontinuities, where like we have this events that happen and then 2 years and they don't happen again, and you have situations like that, your analysis of scenarios and your scenario selection might not capture situations that are important for your stakeholders again. So it doesn't matter if you run 1,000 or 1,000,000 scenarios, you still will be able to have situations that your probabilistic analysis can capture it correctly. So there has to be a continuous balance of how much uncertainty we want to introduce in the system and how reliable the representation is in our Monte Carlo approaches, especially when it comes to capturing events that have significant impacts. Let's go to the next slide. Right, so, and this brings me to the other component of the equation, right? We discussed so far some probabilities. Now we're talking about the exposure representation. What is my system modeling approach? So if we understand that the system modeling choices have to be able to represent the capacity of the system of absorbing the event, recovering from the event, and then adapting to it, then we can actually start understanding what do we need to put into the details of our system operation that is able to characterize this process. So the choices about system representation are critical to determine if we can actually deliver that capacity. So we have in modern resource adequacy questions, we're actually trying to answer two questions. One question is the capacity available? Yes or no? And the second question is, can my system deliver that capacity? So do we have a deliverability challenge, which could be driven by how do we use the storage, is the transmission capacity or not? So it is important that part of the process allows the modeler and the analysis to say, if I'm looking into a short-term, next 2 years resource adequacy challenge, I need to be really looking into my deliverability because I need to make very short-term changes in operations or investments to look into that. As I'm looking ahead into my planning 10 years ahead, the uncertainty of the system and the fleet and all the things that happen kind dominate on top of the details of deliverability. So it doesn't mean that it is not important, but it's not as critical to decide exactly if should I include ramps, minimum up and downs, and gas availabilities or not. So let's look ahead to the next slide. Right, so this exposure representation, again, we can put it in a continuum that goes between this classical probabilistic, like a tool called like PRAS, where there is no actual dispatch, and there's no intertemporal correlations, and there's no transmission network. And we can see that if we actually model that, we can get some information about how many hour event years we get, and we can go all the way to the other extreme, where we actually have a large amount of detail that goes into the system where we run multiple stages, your UC-ED, and it has a dispatch approach that includes multi-stage simulations with the representation of the network. So again, for this particular analysis in the system in the paper that we studied, you can see that the more information we capture about how the system recovers and how the system responds to an event, the more likelihood that we can capture potential hours of unserved load we get. And the more simplistic the system, the least likely that we can capture situations where deliverability is a big problem. So again, the exposure representation allows us to balance the needs in a study depending on how far ahead in the future and the conditions that we need to be. So let's go to the next slide. And one of the biggest topics recently is also what is the effect of transmission in the resource adequacy space? How much can we, quote unquote, take advantage of other regions' capacity or spare capacity to fix capacity problems in a particular other ISO? And again, this just increases the need to include more details into an exposure problem, because now we need to understand if the transmission capacity has to deliver new resources to the network. Can that create new violations of ratings? Can it create actually now another set of risks on the transmission system if we're relying on long periods of time where transactions over the AC network are part of our resource adequacy strategy? So again, this is like the classical saying that says that there is no riskless way to reduce risk. So you can actually reduce, in many cases, through analysis of transmission systems, accounting for them within your resource adequacy. You can include more resource adequacy assets from different regions, but you have to take into account how can that elevate or change the makeup of the risk for your transmission system. So I think that it is important to continuously have to thread this needle of how much detail goes into my models, how much exposure do I care about, and what are the important pieces that matter for my stakeholders. You might live in a state where the stakeholders say, I don't want to rely on imports as much as I would like to for my resource adequacy, which implies more build out and investment local to your particular state. And in the same way, you can have the opposite that says, I already live in a region that relies on transactions for resource adequacy. I should reinforce my transmission system, yes or no. So again, if you take this risk assessment perspective on resource adequacy, you realize that there's a lot of levers that can be moved, and it all matters to like what are the objectives locally to your location and what are the objectives of your stakeholders. So let's go to the next slide. Now I'm going to leave it with Sebastian to discuss some of the most important metrics when it comes to deciding if your system is resource adequate or not.
Thank you, Jose. One final remark about resource adequacy metrics is that traditionally resource adequacy criteria used a loss of load expectation of 1 day event in 10 years as the standard benchmark. We need to be aware that this was established before hourly resource adequacy simulation models became common. So with the introduction of hourly resource adequacy simulations, engineers often translated the traditional criteria of into 24-hour events per 10 years, which is equivalent to 2.4 event hours per year. But however, these translations does not preserve the same reliability standard. So for instance, in the top figure, you can see that cases A, B, and D all satisfy 1 day event of loss of load expectation. But if you see in the hourly, in our events, those events are radically different. So the key takeaway here is that you cannot convert directly. You cannot make that conversion from day events to hour events in this loss of load expectation metric. And also in the figure below, we also have different events that have the same loss of load expectation, but those are different events actually. So the second key takeaway from this slide is that single resource adequacy metrics, such as loss of load expectation, provides useful information, but it's not enough. You need like a complete set of reliability metrics to do an assessment and to really understand what is going on in your system. So we can pass to the next slide, and I will pass over my colleagues of PNNL. Go ahead, please.
Thanks. Great. So with that introduction to resource adequacy and the metrics, I'm going to dive into a little preview into capacity accreditation within resource adequacy. So capacity accreditation is going to be the piece that impacts the quantity of the resources that are going to be allowed to be added to the system. I want to walk you through this flow chart for a moment first, so that we can see where capacity accreditation, capacity credits come into play and how those are going to be impacting resource adequacy assessments. So there's a lot of relationships between capacity expansion modeling and resource adequacy modeling. The color coding here is that everything in teal is capacity expansion based. Everything in green is a resource adequacy model. So the capacity expansion model has some assumptions about policy targets, economic dispatch, optimization for new generation, but is only for a few days. And then that is going to produce a future infrastructure that is then tested by your resource adequacy model. Where the resource adequacy model now has insight into lots of weather variability, forced outage rates, with the goal of minimizing unserved energy, and is done for a full year. Now, resource adequacy outputs are, your metrics such as your loss of load expectation. If you do not hit that target, then you need to either increase your planning reserve margin, and then update your capacity credits. So throughout this process, I hope one takeaway that you have here is that the accreditation is a D rate for the capacity for each resource that is then fed into the capacity expansion model. And then within the RA model, the full capacity, I just want to underline that. So we've derated the capacity of the individual resource in capacity expansion because we're only looking at a slice of that resource's production. But then in resource adequacy, we don't derate the capacity because we use the full time series. So we're looking at the 8760. Next slide, please. The capacity credits that are used in this updated regime, they can be updated within the capacity expansion modeling framework, or they could be held static from external calculations. One example of this would be for all of the imaginable permutations of your future policies, your future generation mix, what would the contribution of that resource be? And then you would have what would be called an ELCC surface, an effective load carrying capacity surface. And then you pluck your value from that surface so you don't have to update as you go. So the capacity accreditation is going to determine the allowed resource certification for capacity payments, which are critical for short-term RA planning. So although capacity accreditation is kind of like an input into your capacity expansion modeling, and then it does impact the amount of resources that you are now checking for adequacy in your modeling step, it's important to remember that the capacity accreditation is also the piece in operational planning where your resources are getting paid for their resource adequacy. So pretty important piece there. Next slide. And then I just want to remind folks that the last presentation in this series is going to be a deep dive into capacity accreditation. So this is the evolution of resource accreditation on December 2nd, given by my colleague Travis Duvell from PNL. Next slide, please. Now I'll touch a little bit on the popular modeling tools in industry for resource adequacy. There are, let's say, 4 dominant tools that are used by stakeholders and developed by industry. And by that, I mean that for the most part, they are black box tools that, to work with a particular developer. So for example, Servum is developed by PowerGem, which used to be Astrop Bay Consulting. GE Mars, which is now called PlanOS Resource Adequacy, is developed by GE Vernova. Prism is an in-house tool to PJM. I've included this here because, it is black box to everyone outside of PJM, but it's modeled a little bit off of Mars. Then Plexos is developed by Energy Exemplar. These tools have different assumptions for the planning regions. Obviously there's a lot of different nuances to these tools, but when we think about, one of my colleagues was talking about transmission and considerations for that. Usually these analyses are done in a zonal fashion or multi-areas. And so I wanted to give you a little bit of some detail on how these industry tools treat the transmission or cross area, cross zone transmission. So for example, in Prism, which is the example on the left here for PJM, it treats everything as if it's 2 areas. So there's PJM and then there's the rest of the world. And then everything outside of the rest of the world there is a non-modeled region. So they're only considering their capacity within PJM and then transfers outside of PJM. But other tools, the other ones I mentioned here, are multi-area, so they might have like, more than 2 zones, let's say. They can transfer capacity across the zones. Okay, next slide, please. There are a handful of dominant open source modeling tools. So for example, there's a tool called GridPath that's been developed by Sylvan Energy Analytics. And there are, while I was putting these slides together, I thought of also including some examples of important reports that have been put out. But frankly, there are a ton of really relevant reports from all of these tools. And so it felt a little bit difficult to be exhaustive there. But if you're in the regulator space and deal with IOUs, then you probably have familiarity with, even if you don't realize it, with a number of these tools. So GridPath, they work with a number of utilities, especially in the west of the United States. PRAS is a tool developed by NREL, the Probabilistic Resource Adequacy Suite. And again, this has been used for a number of studies. Progress is a more recent tool that's been developed by Sandia National Lab. And then the final one, which is developed by RTE, the French Electric Transmission System Operator, and TARES, is developed by a non-US developer. However, there are some studies that have been conducted with this tool from the United States. And so for that reason, I've included it here. And it is open source. Alongside open source modeling tools, if you are relying on an open source model, you probably are also looking for open source data sets. So we thought it'd be helpful to include some insights there. Some commonly available data sets would be that for resource outages from NERC. So you want to know about resource outages for generation, that would be from GADS, and from transmission, that's TADS, so the transmission availability data system. You also want to have some understanding of projections of retirements and installed capacities over time. That can come from the EIA 860 datasets. And then for variable resource time series, we would direct you to the NREL Wind Toolkit and the National Solar Radiation Database. Next slide. A few considerations to look at here. So I'm going to talk about 2 details. One let's start first with large loads. So if we are looking at how to consider large loads in resource adequacy, this is going to be done in the scenario development step. I have a visualization that I've developed that's on the right here that I used in a previous presentation in this series. So you can imagine it kind of looks like a Rubik's Cube, but then there's like 9 Rubik's Cubes. Within that, you have a little box. So one of these boxes, let's call that all of the data you need for 1 year of analysis. So let's say it's one entire little data set, and that can tell you what the hours of outage are. And that's also one draw from your distribution for forced outage rates. So it is one simulation. But in general, with resource adequacy, we incorporate a slew of dimensions. I've only included here 40 weather years. I have some dimensionality for maybe different stages of your capacity expansion. That's the different colors in here. And then different load growth scenarios. So imagining that your basic load will grow in different ways, but then perhaps you also want to vary your large load assumptions. So that varying of the large load assumption is going to be just another scenario you want to look at. So each of these scenarios runs will consider different weather, large load assumptions, load growth over time. This is going to slot into your load forecast in that figure on the bottom, which impacts your transmission planning, resource adequacy evaluation, and your resource planning or capacity expansion. Altogether, this will be hundreds to thousands of scenarios simply by varying your large load build-out assumptions. Next slide. I'm also going to touch briefly on considerations for generation retirement. Generator retirement assumptions will be fed into your capacity expansion. This is going to be an input to capacity expansion or resource planning in our flowchart. Retirements and rates of retirements are often policy informed, and that's why they are going to be modeled within capacity expansion. So it's an assumption or a scenario in that model step. There's two types of retirement that you can consider. The first is exogenous. So perhaps you know that a handful of generators are going to be retired because it's been announced, or the anticipated retirement, or perhaps you want to use an assumed end of life for a specific class of resources. The other way to model generation retirement is endogenously, meaning within your model. So perhaps you have a way to determine within the capacity expansion model based on economic retirement of units, and then they are simply retired within the model itself. So that's it for my contributions. Thank you, and I'll pass it off to my colleagues.
Thank you, Alison. Well, now this section gives a practical overview of how resource adequacy assessments are developed in the United States and what state agencies and regulators should focus on when reading them. Who publishes these assessments varies by region. In ISO and RTO footprints, the system operator does. In the non-market West, utilities and the Western Resource Adequacy Program coordinate studies under WEC oversight. In the Southeast and Florida, utilities conduct their own studies under the CERC umbrella, and Alaska and Hawaii use utility level processes. The covers on the slide from MISO, PJM, CAISO, and WEC show the variety you will encounter. Now let us look at who does what and how across regions. In the US, resource adequacy is organized in several ways. Uncertainty and exposure definitions in resource adequacy studies change significantly between regions, stakeholders, and operating practices. The diversity of requirements makes it almost impossible to compare across approaches and select the correct one. However, there are important aspects to how to interpret these practices. In ISO and RTO regions, such as PJM, MISO, New York ISO, ISO New England, CAISO, SPP, and ERCOT, the operator publishes the assessment, sets the reserve requirements, accredits resources, and converts results into capacity obligations. In the non-market West, utilities and RAP coordinate resource adequacy under WEC oversight with utility or program studies that reference regional standards and transfer limits. In the Southeast and Florida, there is no ISO, and utilities conduct resource adequacy work with a commission review and CERC oversight, and obligations flow through utility procurement and integrated planning. And Alaska and Hawaii are utility level as well. Well, with that structure in mind, here is how to read an assessment in practice. The first thing we recommend is to ground the context. Pay attention to the footprint, study horizon, and the target standard. Many regions use the 1 day in 10 years target, and some also report event counts or energy at risk. 2, trace how analysis becomes obligations. The load forecast fits a reserve requirement, such as installed reserve margin or planning reserve margin. Resources are accredited, often using effective load carrying capacity or ELCC, and accredited capacity translates into obligations or procurement that affect customers' cost. Third, keep adequacy and operation separate. Adequacy asks whether enough capacity exists under uncertainty, and operational risks ask whether commitment, dispatch, transmission limits, fuel deliverability, and forecast error allow delivery hour by hour. And fourth, Keep a state lens. Check alignment with policy goals, local reliability drivers like winter risk or data center growth, and affordability. If fuel deliverability, long duration storage behavior, or transmission outages are outside scope, flag them for follow-up. Now, metrics. Each metric answers a different questions. Loss of load expectation shows how often shortfalls are expected to occur in days per year. Loss of load hours shows how long they last in hours per year. Unexpected unserved energy and expected energy not served show the magnitude in megawatt hours per year of these outages. Location and season matter because remedies and costs differ. For example, for winter evening risks is different, very different versus scattered summer events. Also, methods should reflect today's drivers of risk. Probabilistic and chronological modeling captures multi-day heat, extended winter events, storage cycling, ramp limits, forecast error, and correlated outages. Also, a single peak hour margin can miss multi-hour scarcity and overstate what short duration storage or fast start units can do. And finally, accreditation connects metrics to what counts toward the requirement. Effective load carrying capability for wind, solar, storage, and hybrids reflects reliability value rather than nameplate. Credits often decline as fleet grows and may vary by season and sun. So large addition of one resources can lower its marginal credit. Well, and also talking about inputs and common red flags, results are often driven by a few inputs. Load needs to reflect building and transport electrification, new large loads such as data centers, also enough weather years, and representation of extremes. Missing fast growth tends to understate both loss of load hours and expected unserved energy. Outages require correlated force outage modeling and explicit treatment of winter performance and fuel deliverability. Without that detail, winter risk is often understated. Also, variable renewables and storage depend on credible profiles and operational limits. Check profile resources and geographic correlation. And for storage, duration, round trip efficiency, and state of charge limits are decisive. Also, in the case of hybrid systems, they need clear operating rules because those rules affect accreditation and operations. And transmission and inputs must be validated, confirm interface limits, plan outages on key paths, and how type benefits were obtained. And also, if imports are relied upon during stress, there should be evidence that they are available and deliverable when neighbors are also stressed. Common red flags include out-of-date load forecasts, ELCC values that stay fixed while fleets grow, teen winter sensitivities without correlated outage modeling or gas constraints, also heavy reliance on imports without deliverability tests, and entry or retirement assumptions that do not match interconnection status. Any of these can materially move adequacy metrics. Well, let's use the example of PJM to show how the pieces connect. The RA study sets the installed reserve margin, which is translated into the forecast pool requirement. That requirement shapes the variable resource requirement demand curve in the capacity construct, and auctions clear against this curve to create locational obligations and costs. ELCC then determines how much accredited capacity each resource type contributes towards those obligations. On metrics, loss of load expectation remains the anchor for frequency, and expected unserved energy provides the magnitude view, which separates portfolios that have similar LOLE but very different energy at risk. What to watch now includes winter risks with correlated thermal outages, fuel deliverability during cold events, and changing accreditation as storage and renewables scale. The same review lens applies in other regions, even if the labels differ. And that's a very high-level overview of how to read an RA assessment. Thank you for your attention, and I give the floor back to Pete for closing remarks.
All right, thanks, Rafael, Allison, Sebastian, Jose. Really appreciate all the material you presented today. If you could go to the last slide, I just wanted to make people aware that this series of webinars actually came out of some requests for technical assistance by a number of states on the topic of forecasting and resource adequacy. We received those requests through our website. We have multiple types of technical assistance that can be provided that really differs by sort of the level or depth of need. So our help desk requests are pretty quick turnaround, 4 hours of support, really asking Rafael or Allison some quick questions. Maybe they've got a presentation already canned that they can, provide to you. Next up, we've got our expert match. This can provide up to 100 person hours of support. Obviously allows for some more development of materials, maybe some very, very short analysis or review of materials, but ultimately, it's really limited to that 100 hours. Our last opportunity here is called Deep Dive. This is one that typically will span 6 to 9 to 12 months. Unfortunately, it is one we currently are not offering, but hopefully will, depending on the next fiscal year funding that's allocated to this program. So please keep your eyes open for that. All of the information associated with this technical assistance program and the webinars themselves can be found at that URL on the left-hand side there, and you can access it through the QR code on the left as well. We will be posting a recording of this. Oh, you actually found it. We probably here. So with that, let me close things out. Thank you for listening to this webinar. And on the last slide, we've got contact information for all the presenters today and those who developed the material. Please feel free to reach out to them if you have any questions. So with that, thank you all very much, and hopefully you can listen into some of the other webinars in this series.